as we already announced a little bit earlier, we want to take a little bit deeper dive into lens data, what lens data we typically use with our customers to help them make a decision between one or the other lens and trying to find the ideal lens for the application. So first, how do you really tell which one is the better lens, right? We have a picture here with a couple of Sunix lenses as an example. What do you go by? Is it the size of the lens? Is it the number of elements that are inside the optical stack? Is it maybe material choice, right? Do you want to have a glass lens, or does your application maybe require a hybrid lens where we combine aspherical injection molded plastic elements with traditional spherical glass elements? Is it defined by cost? So what is really the factor that you would choose to say that is the best lens? If you take a little bit different view at the same question, quite often people associate performance and specs with cost, and quite often it transitions from being all plastic through hybrid lenses, glass lenses, and I've listed here complex glass. Just let's assume that it's a glass lens with lots of elements in there, until we reach this point where we have an all glass lens that also has aspherical molded glass elements in there. So is that the view? And what we think, it's not just this one curve, it's actually more an area that you have to look at. Because depending on specific requirements or specs, right, you could maybe have a hybrid lens that if you compare kind of apples to apples is maybe more performant than a glass lens that was never tuned for a particular application. So it's very important to kind of separate yourself from some of the maybe assumptions that are out there and really discuss some of those application details with us in particular to really find out what is the best lens for you. Important, we really play in this entire area. We maybe do less all plastic lenses, but whether you go from a hybrid lens to a very complex and molded glass lens, we deliver on this entire area. Then maybe the first question for you, if you look at this surface area that I was showing here now, so is the best lens always in the top right corner?
No, not necessarily. You know, as we have already discussed, you know, best in air quotes is a relative thing, but in general, the best lens or the highest performance lens is really tied to performance more than it is material, and by extension, I think that can be related to the tolerances that are required. So a plastic lens, an all plastic lens with very tight tolerances and very high performance may actually cost more than a glass lens or a glass asphere lens. Now, that being said, all other things being equal, which in optics they usually aren't, but if we assume that two lenses have the same performance and the same tolerance, then yes, material plays a role, and glass will generally be more expensive than plastic. But I think the first order driver for cost is always performance and tolerance as it relates to that performance.
Yeah, and not to mention, right, we have always mentioned that already in other webinars as well, but obviously the yearly volume has also a big impact in cost, right, in sourcing raw materials. So that
yeah, and manufacturing, the volume is a first order driver for sure.
Yeah. There's another view to this entire what is actually the best lens, right? And it probably starts off with your own program, right? Requirements that are key from your view, from the way you define things for a good program, right? Whether that is a sensor partner you already picked, whether that's a form factor where the lens has to fit in, the field of use you want to achieve, the cost target you have, right? Or maybe also the timelines that you have, right? In that particular case, we maybe could design the perfect lens for your program, but that will require some time. So maybe in that case, if the timelines are very tight and short, an off-the-shelf lens that is already there and readily available might be the better choice, right? So it really, what I had on the previous slides, it really depends. There's a couple of other things, right? If you look at lens data, and we already spoke to that, there's so many different first and second order lens parameters that flow into making the decision ultimately, which is the best lens for a particular program. And this is typically what we discuss in a dialogue very early on, right? Whether you want to call it design review officially or just exchanging lens data, this is something that happens early on and should give the high level direction and being able to filter down some of the possible lenses to the 2 or 3 recommended candidates that you maybe want to look and take a closer look at. But there's another thing that is like not only lens data, but also where the lens is used in, right? It's very different if the use case for the lens is an indoor application where this may be an outdoor application where the lens is also in a more rugged environment. So environmental and reliability requirements also bring some challenges to the table that need to be considered, maybe not in the very first dialogue, but we typically ask those questions very early on to make sure also we consider that, right? And environmental and reliability kind of tailors a little bit the application space. And this is something that we then prove and show in the reliability testing where the lens then goes through all those different procedures. And when this all comes together, right, and if we speak in the terminology of maybe a project timeline, right, then we start going into process validation, production part approval process until we eventually have the moment that we can start the start of production. So all those things eventually have to come together, and together they will determine which is the right lens for the right program. What we want to do today is we focus more on the lens data side, right? On the early stage. If you have a couple of different choices, what are key data and key parameters you should actually look at to maybe filter it further down and to be very efficient in this selection process. For the selection process as well, and the screenshot here is relating to that a little bit. One of the very first webinars we recorded a couple of weeks ago was how to pick the right lens for my project. Right, and those optical visits that you see here on sunx.com, they're very, very helpful to guide you through. And from the hundreds of designs that we have online and available, that you can actually boil it down to maybe 5 or 10 that in a closer selection. And then you can simply look at the data sheets that we have online for you and look at key first order parameters of this lens. And we recommended in the past that this is maybe a very good point to start a dialogue with us and maybe filter it down further. So again, if you go on sunx.com/webinars or to our YouTube channel, you will find those webinars, and I hope that they will be a good resource for you in this first step. The next logical step is then, okay, let's talk in more detail about, right? If we boiled it down to maybe 2 or 3, then we want to already look at more specific data. And I just put a word cloud in here because there's so many data you can sometimes even get lost in and get into the weeds about. To really try to find the right lens. But what we think is there's maybe 3 or 4 key things in the beginning, right? MTF, through focus, relative illumination, and distortion that give you a very, very good idea if you compare them across 2 or 3 lenses where you think, okay, I can maybe eliminate another possible lens and boil it down to 2. Because in the end, everybody also needs to be efficient with the time that we have, right, to help you towards the right selection. Ben, in your experience, right, you definitely have a very long experience. How often do you see that those 3 or 4 key performance data here will be helpful in the initial discussions?
These are definitely the top ones that we see. Once you finish talking about what's the field of view and F number and, you know, what we call the first order lens characteristics, as far as performance goes, the very next thing we talk about with most customers is MTF, specifically MTF and relative illumination, and then distortion and through focus, probably in that order. These are certainly not, the full suite of possibilities with regard to lens performance, and especially for imaging, these are important. But we also do some non-imaging applications, and for that, we might talk about spot size or transmission, and those things are important to imaging as well. But by and large, for the imaging applications that we do, these 4 come up time and time again. And so, if you're just learning about optics, or if you're just engaging in a new discussion about custom optics, or even about an off-the-shelf optic with a supplier, these are the 4 that are going to have a big impact on your image quality out of the gate.
Yeah. Okay. And right before I was introducing our special guest, so I don't want to be unfair and hold Natalie back for too long. I just want to give you like just 4 more slides, just quickly characterizing and maybe setting the stage a little bit, how we see those 4 performance data. And then I'll hand it over to Natalie and we'll switch live to ZMAX so she can actually use a sample lens and talk us through some of the data curves. So first, MTF is probably something everybody talks about when looking at a lens. And the reason why is it's a very objective measure of the lens performance. A good thing is also it's purely based on the lens stack data. So it also gives you a good indicator of what you can maybe expect down the road for the first prototypes that will be built. And the reason why MTF is important, right? Because if an optical system is imaging an object from the real world into by now the digital world, right, you will always have some losses, and MTF gives you a good idea about the lens performance overall. And again, it's a very fair comparison across several lenses, or even in that case also suppliers that maybe answer to the same RFQ. Another very important curve that we use very often is the through focus MTF. Here again, for a particular spatial frequency, or in that case also maybe for particular temperatures, you just look how MTF performance changes over the various field angles relative to a best focus position. And depth of focus is one of the key parameters that we're always taking out of this type of graph when we discuss lens performance with our customers. Relative illumination, again, not to confuse with total transmissivity of a lens or an optical stack. It's just a measure of how much the light will fall off from the on axis to the far field. Again, also a very important measure to, especially when you use software algorithms, to make sure that your software algorithm can deal with a relative illumination drop from on axis to the field. And as I mentioned before, Natalie will show this live as well, and we go in some more of the details. And then the final data set that we want to look at is distortion, a very key profile for many applications and industries. And as you probably know, and again, we also recorded a webinar totally dedicated to distortion, our tailored distortion technologies. You have different distortion methods and algorithms, right? So it's always important to understand kind of what distortion profile you're actually referencing, and then to understand what's the percentage difference of that particular lens to a given distortion model. And what we then provide to customers is something maybe less the field curvature on the left side here, but you see the distortion profile there on the right side for a particular lens. And Natalie will also show that for the sample lens that we have picked. So without further delays, at this time, I want to hand it over to Natalie, and she will take us straight to ZMAX.
Hi everyone, so thank you Ingo for that introduction. I will share my screen now. It's my direct ZMAX screen, and so we can go by example through some of the plots. So sharing screen. One moment. One moment, sorry, just ensuring it's terminated.
Yep.
Can I browse my ZMAX window? Yes?
Absolutely.
Yes, we can.
Great. So what I have here is an example lens that we've chosen just to show a couple of the plots, gain a little more familiarity. So what I have here is an MTF versus field plot. So this is to what Ingo was mentioning with MTF. This allows us to gain an understanding of the contrast and resolution of a particular system. And this is just one way of characterizing MTF. So it's MTF versus field in this case.
Mm-hmm. Can I ask a quick question? You have like two curves in there, a blue one and a green one. I see at the bottom there, they represent different frequencies.
Yes.
When would you use just one or more? Why do we have different ones in here?
Right. So exactly, these are the different spatial frequencies. The spatial frequency that is being used to evaluate a lens system really depends on the sensor and the pixel size that is being used. So every sensor has what's called a Nyquist limit, which is the limiting resolution of a sensor. Through a mathematical equation, this is a direct correlation to the pixel size. Typically, we use the half Nyquist. So we use half of the Nyquist limit that we calculate, just because this is a typical standard methodology for test equipment. So in this case, for example, if we're evaluating the green line, which is 83, for example, cycles per millimeter, this might be assuming a monochrome sensor of 3 micron pixel pitch, for example. And so this would be the half Nyquist of that. In the same way, the blue line I'm just showing for reference. This might be the half Nyquist of a 1.55 micron pixel pitch. And as we can see, as the higher the spatial frequency, the more the MTF drops. So this is just to provide a perspective of two different ways to analyze it. Someone that might be analyzing this lens for whether it's a 3 micron sensor using the 83 line pairs chart, the green line, or someone that might be using it for an even smaller pixel size.
Okay, thank you.
So MTF versus field, another way that we can present the MTF data, and I've just generated this ahead of time, but this is MTF versus the frequency. So in essence, this is the same type of data we're presenting. It's just presented in a different format. The data is still characterizing the lens in the same way.
So if on the right chart, if I look at the 0-degree curve, which I think is the blue one, right? If I would pick a 83 line pairs per millimeter, I should get the same data point which I see on the left side, right?
Yes, absolutely. That's right.
And Ben, between the two, right? If they show similar data, when would you use one or the other?
Yeah, that's a good question. And again, it's important to reiterate that they show the same information, but in slightly different format or ways. And I personally find the MTF versus field graph on the left very useful for seeing how flat the response is for the lens across the field. So that's useful, and that's at a particular spatial frequency. So if, for example, you know the spatial frequency that you want to see how flat the response curve is across the field of the lens, this is a very quick and intuitive way to view how that lens, how good that lens is performing or efficient from center to edge of the field, as opposed to the MTF versus spatial frequency might be more useful, for example, for judging the absolute performance. In other words, how good is that lens up to the maximum, say, Nyquist frequency of the sensor that you're using. So same data presented in two different ways, depending on what you're interested in. And these things aren't mutually exclusive, of course. We can provide both sets of data, but that's how you might use them, one different from the other.
Thank you.
Okay. I think after this, we will move on to the MTF true focus to get an understanding of this one. So here I have pre-generated the MTF true focus plot. Similar to how we just evaluated MTF versus field, MTF versus spatial frequency, this is still evaluating MTF. You can still extrapolate the same points. It's also just a different way to characterize the system.
And I assume if you would have now two different lenses, right, that you would right away, based in a split second, see how they would differ, right? If, for instance, all those field curves are not perfectly overlaying, almost like here, right? So you could really see visually right away how two lenses would be different from each other.
Right. Yes, absolutely.
And another question to this one, and I think I mentioned it before in my overview slides. Depth of focus is in some application for some customers an important data point. Can you quickly just allude to that? How would we look at depth of focus here? How would we use this graph for maybe looking at depth of focus?
Right. So the depth of focus here, maybe just to prequel it, and as we've touched on already, the main things that we're looking for here is that the peaks are high and that they're overlapped. And what we mean by depth of focus is that if the peaks are aligned, this is essentially the focal position of that field point. And so when we are looking, for example, whether a lens will be in focus with a shift, for example, whether it's a thermal shift, whether it's maybe a misalignment in regards to the sensor, whether it could be even relating to depth of field. For example, if you have a certain object distance, our image plane, our natural image plane will want to shift. And by this token, then we need to evaluate, for example, whether these curves will still be in focus. And so I was thinking maybe if we wanted to run a quick example, if we are looking where the black line here hits, and we're looking at the on-axis point 0 degrees, we can see MTF on axis is about 77% here. And so in this way, and this is assuming infinite conjugates. If we want to assume an object is placed at 500 millimeters, we can see now how the focus plane would shift. And if we could just give it a moment to load. So we can see that all of these curves shifted now. You could see that this blue line, which is the on-axis point, now shifted by about 16 microns. It's no longer centered with this black line. And so that means that if we were able to refocus the lens, ideally we would put our image plane location 16 microns away from what we had it previously. That being said, if we're evaluating this lens now, and we just want to see, okay, we've moved our object, is this lens still going to perform? We can see that the on-axis MTF is still about 62%, which I think for most applications would totally suffice. So this is one way of using data, just to see by how much does the nominal image plane move, whether it's because of an object distance, whether it's because these curves naturally shift with temperature, whether it's because of the alignment of the sensor. So it's one way of seeing, are we still in focus or would the lens need to be readjusted?
Okay. So you basically, the space underneath the curve, right? How much that is opening up, that kind of gives you, right, whatever is your minimum MTF, if I, oh, that's not a very nice line, but if I draw this, right, whatever is your minimum MTF you can accept, right, that space when one field curve or the other ones are touching, that kind of gives you the amount the lens could actually shift due to temperature, or what you just mentioned before, maybe due to process tolerancing or something, right?
Yes, exactly.
There's one more thing I noticed at the previous graphs as well, and at this one, right? It says the data for 470 to 650 wavelengths. So when would you adjust wavelengths for such a graph, or also the MTF graph we saw before? 470 to 650 nanometers here in this case.
Right. So exactly, in this case, we're just evaluating the lens in the photopic spectrum, just the visible spectrum. This lens, when it was first designed, was probably with the intention of functioning the visible spectrum. Now, for example, we can assume that depending on the exact application, there might be a different light source. For example, instead of visible, maybe there's certain applications that also need to use a lens at near infrared or at 850 nanometers. And in this case, of course, we would adjust the wavelength. We'd want to, for example, evaluate how does the lens perform at that wavelength. And what's important to consider here, and why the true focus plot is important, is that if we now change the analysis wavelength from visible to, for example, 850, if this lens wasn't initially designed for 850 nanometers, these peaks would shift. And what that means is that the ideal focal plane would shift. Mm-hmm. In an ideal sense, the lens would have to be refocused by some means. And the benefit is, and alternatively though, we do have, let's say, hyperspectral lenses. And what this means is that the lens is optimized not only for visible, but at the same time visible plus 850, for example, or plus 940, or whichever near infrared wavelength. Okay. And this allows the lens to optimally function throughout that broadband wavelength range without the need to have to refocus the lens, which can get complicated depending if you can manually refocus or actively. So there's benefit to that.
So maybe this MTF true focus is also very helpful if the customer maybe has already good experience with one lens and is already using it in one application and plans to use the same lens for a different application, maybe with a different wavelength spectrum, right? So this would really give a good indicator whether that's possible or maybe not such a good idea and we should look for a different lens.
Yes, exactly.
Good. So what about relative illumination? Let's move on to the next one.
Relative illumination. So relative illumination. So the relative illumination is used as an indicator. It shows the efficiency of transmitting the light from the center of the lens to the edge. As the name implies, it is relative. It's not an absolute measurement. But why this is important is because the human eye and both software can recognize light fall off. And depending on the exact application, the relative illumination percentage, the exact drop off from center to edge may be more critical to evaluate.
You had before the other chart showed the spatial frequency, right? And you explained that the spatial frequency, at least the one that you would pick, is somehow tied to the pixel size of the sensor. Mm-hmm. Why is that not listed here?
Yeah, in this case, the relative illumination isn't so much dependent on the pixel size. It's more correlated to the sensor dimensions. So for example, I think I have distortion graphs here. So for example, if we were to analyze, a 1/3" sensor, which we can assume has a 6 millimeter diagonal, if we wanted to see what the relative illumination is at that diagonal, just to make sure we have enough light there, we would make sure, for example, here on the left, I have just real image height data correlated to angle. We would make sure that at the corner, so at 3 millimeters, just because this is the half sizes, right? This is image height versus image circle. So 3 millimeters corresponds to about 60 degrees field of view. So meaning that we have plus minus 60 degrees at that diagonal, and going here, we just want to make sure that at that 60 degrees, so at 3 millimeter image height, which corresponds to the diagonal of that sensor, we are getting about 81% relative illumination. So it's more of a size comparison, whether you want to evaluate the diagonal of the sensor or if you want the horizontal dimension of the sensor, you would just adjust accordingly using the image height.
Mm-hmm. And Ben, right, we have relative illumination, but it's not to be confused with transmissivity or transmission of the lens, right?
Right, yeah. You'll sometimes see people get those things confused. Total transmission of the lens is different. It's in versus out. This is a comparison of the illumination at the center of the lens. Usually it's the reference to the center of the lens to the edge. Or in this case, rather just a plot of what that illumination looks like across the field, in this case, the half field. But you'll often hear it referred to as illumination roll-off, like when you talk about, like in the camera space, or if you talk to sensor guys, they'll say illumination roll-off. They might call it sensor shading. It's basically, in optical terms, relative illumination.
And Natalie, you already have there some raw data for distortion open. Let's move to that topic. How does that look like?
Sure. So looking at distortion, and actually I'll switch to Excel. It's the same exact data. I've just extracted it previously and plotted it here for simplicity. So there's different distortion models, whether it's rectilinear, f-tan theta, or f theta. This particular lens has f theta distortion. And typically what we look at with distortion, right, is we correlate the field angle versus the real image height. And distortion, the percentage, is just a direct correlation predicting where does the actual ray land versus where is the predicted height in the distortion model that it should have landed, for example. And that's where this percentage comes from. In this case, as mentioned, we have f theta distortion, but this lens also is what we call Taylor distortion. We've designed the lens in such a way so as to increase the number of pixels per field angle. This typically allows us to have greater resolution near the edges. So this lens in particular has that feature, but there's different models, there's different distortion profiles based on the application.
So that is why the graph is not plateauing, right? It keeps going.
Yeah.
And this is easy to see in the graph. So why would I use the raw data as well if I can nicely visually see in the graph the actual distortion profile. So when would I use the graph? And again, we see raw data here.
Yeah, well, the graph is a good quick glance especially for looking at maximum distortion at the image circle. And of course, again, it's the same data, but if you're comparing one lens to another lens or multiple lenses, it's much easier to just look at the graph and say, okay, this lens has X amount of distortion, that lens has Y amount of distortion. But when you're working with a particular lens, and once you've chosen a lens, the tabulated data becomes very useful for two reasons. First, it allows you to find the actual field of view at any given field point, whether it's the horizontal, vertical, or any region of interest. The second reason that tabulated data is important, and the reason we provide it to customers is because this gives you effectively the coordinates for doing a D-warp. If the lens is an F theta and you want to remap it or D-warp it, to, let's say, rectilinear or some other projection, you can use this data to do that on a very fine-grained level with high resolution. So those would be the two reasons you might want the tabulated data. Okay.
And Natalie, if you don't mind, I'll take over screen sharing again to bring this to an end. And I really want to thank you for joining today, because I can ask a lot of questions, but it's great to have someone here who can actually really give the professional and detailed technical answers. So thanks a lot for joining today.
Thank you.
So there's maybe just one more thing. There's a couple of other considerations as well, right? So what we have seen sometimes, that the sensor part number gets picked very early, and in that case, sometimes too early. Because if you lock yourself in with a sensor, you might not have the complete freedom of choosing a good lens. So one recommendations we can make is really, if you want to, especially if you want to choose an off-the-shelf lens, maybe pick 2 or 3, maybe 4 different sensors you would consider, and then look at the 1 or 2 or 3 off-the-shelf lenses you would consider for your application, and just see where's the best overlay, right? Because then you can maybe really move forward with your intent of using an off-the-shelf lens. So don't lock yourself in too early with a sensor selection. It also, right, it still holds up. Typically, you get what you pay for. So typically, cheaper is never better. So, right, there is some cost consideration that goes into lens performance and quality that will play a role eventually. And then there's also what we just showed, right? Design nominal lens data to judge the performance. So when you go through the processes now of maybe you have certain material tolerances, you for sure have some manufacturing tolerances that are different from supplier to supplier. And then also, right, you can't forget, you use lens data, then you connect a sensor to it, and in the end, you have a camera level system as well. So the lens level performance data versus the system, the camera level performance data will also have a variance in there. So that's definitely to be important to always acknowledge that this is taken into consideration. Ben, again, with your experience, right, we showed now several key lens performance data. In your experience, which ones are the ones that are maybe more sensitive to tolerancing and this topic of nominal design versus later as-built performance?
Yeah, that's a really good question. And it's important to have the proper expectations of the design versus the as-built parts. And you know, it's not always clearly understood that lens design and manufacture is very much an analog kind of endeavor, as opposed to, you know, here's the spec and then the lens exactly meets, you know, like say a sensor board perhaps, or a CMOS sensor. You always get some performance degradation in manufacture, and some specifications are more effective than others. Some characteristics like relative illumination and distortion don't actually change very much from the design to the production, and you can generally rely on them being pretty close to the design value. Other values, in particular MTF, are very sensitive to the tolerances, particularly things like tilt and decenter. And basically, you can design a perfect system on paper, but when you put it together, you have to be concerned with tolerances. So with MTF in particular is the big one that we see. You should expect a little bit of degradation in the as-built design. How much is not a simple question to answer. It really is a case-by-case thing, and it's very much related to the performance and the tolerances of the design itself. So something that's very tolerant or something that's not performing at a very high level, you may not see much degradation at all, whereas something that's designed to be very high performing with very tight tolerances, it's going to have more of a population distribution in manufacturing.
Okay. Good. And with that, so thanks for bringing this together, Ben. And we're like at our last two slides, and they're always the same slides because they're always holding up and they're true, right? So we can only recommend use the resources that we're providing, either through our optical visits online, to the webinars that we recorded now, boil it down to a pre-selection that you're looking at, and then really get in contact with us, discuss the project. We'll probably ask some questions that you were wondering why we're asking them, right? But what I showed before, we're already trying to think ahead, say, okay, selecting the lens, one, is okay, but two, where do you want to actually put the lens into, right? Is it indoors, is it outdoors? So we're asking those questions early on to make sure we can make the right recommendation. And then we looked at a lot of nominal data, but in the end, it comes down to putting the lens, putting a test sample onto your camera and taking pictures and looking and comparing the picture quality with some of the other lenses you may be considering. And iterating over this dialogue with us, I think it's very key to finding the right lens for your project. Here, as always, our general contact data for Sunix, also Ben's and my direct email addresses if you want to get in contact with us through email or maybe LinkedIn. And again, at this point, I want to thank you for joining us today and for your attendance and spending the time with us. Ben, do we have anything in the Q&As?
I think we've answered everything so far, but as we normally do, we'll leave it open for another minute or so. If anybody has any questions or last thoughts, feel free.
Good. Again, please use the Q&A, type in your questions. We can answer them directly here in the next couple of minutes. We stay online, or we can follow up later by email with you. In respect to everybody's time, we'll conclude the official part of the webinar here. And again, thanks for joining us today.
Thank you, everybody.
Thank you.
Oh, we have a couple of questions here, so let's see. Let's see, the first one is, can we provide black box models of lenses? Generally, this is a good question, actually. We can in certain circumstances, depending on what data you need, we're also happy to provide that data for you. So for example, if you need us to generate some of this data or curves or send you some of the tabulated data, we can certainly do that. So just reach out to us and let us know which lens you're thinking about and what kind of information you need. Let's see. Yeah, and then we got another question here also. Can we comment on relative cost between glass hybrid and molded glasses? This is a good question. It's kind of related to one of your early slides, Ingo. So maybe you want to take that question.
Yeah, so in general, what we already mentioned before, there's a lot of factors that go into what is actually the final piece price of a lens, right? And volume, independent of what structure you pick, volume always has a very, very big impact. And then also, if you talk about glass hybrid and molding glasses, right? There's a couple of factors, because a lens that has multiple elements, they may be all just spherical glass, but this can be more or less cost effective than a lens that maybe has a molded element in there. What you should always consider, if you use molded elements, we typically do that because it allows us and gives us a couple of more degrees of design freedom, because with creating a molded shell shape, you have more options in optimizing the design. Sometimes it's the only way to achieve very, very high field angles for our super fisheye lenses, or maybe bring the overall size down. What you also need to consider is, again, the total volume you may be looking at, because typically a molded lens, whether that is glass, compressing molded or injection molded plastic, spherical elements, they require tooling. So it's really important to understand the entire scope of the project, so that you maybe a higher upfront tooling cost can then easily amortize itself if you have a higher volume, because then the maybe individual lens price is lower, because in the end, plastic is cheaper in the raw material than glass. So again, there's unfortunately not a single answer. That's why I used this graph before. It's not one curve where you can just simply pick one point. It's more a 2 or 3 dimensional space that we need to investigate together with our customers to make sure we have not only the best performing lens, but that it's also from a commercial perspective, the right lens for the right program.
Okay. Thanks, Ingo. That appears to be it for the open questions so far.
Okay, then I would say we thank you for your attention. We stop the webinar here, and you have our contact addresses in here. Please, please, please get in contact with us for any questions you have. Thanks a lot.
Thanks, everyone.